As I said in the intro, what we know about infrared spectroscopy is that certain frequencies of infrared light will interact with certain functional groups at predicted frequencies. So what I'm going to do is I'm going to go through the correlation chart from about 3500 down to about 1500, because in this particular region we can come up with functional groups that will be what I'm calling diagnostic. So what's going to happen is if we see peaks in this region, then we know that we have the functional groups that correspond to those frequencies. If we don't see peaks in these regions, then we can be pretty sure that those functional groups do not exist. Now down here below 1500, in this region, we have a lot of different peaks. It's called the fingerprint region, and we usually don't look for too many peaks down there because they're covered up by others. Alright, so let's continue on. The first one I'd like to talk about is the OH stretch, which we will find in the 3300 to 3500 wave number region. Actually, we'll find OHs, NHs, and NH2s, but the peaks are different shapes, so we'll be able to distinguish them that way. When we're looking at OHs, OH stretches, what I'm talking about here with an OH stretch, is this. So the OH bond moving in and out. That's what we're looking at here. And it turns out that alcohols have fairly broad OH stretches, broad meaning a wide peak, and they are fairly strong, which means they come down a long way. So you'll often hear me use those two terms, broad and sharp, which is going to describe the width of the peak, and weak and strong, which describes how far the peak goes down. Strong would come down here, weak maybe up here. Now there's two OH stretches we're going to see. We're going to see the OH stretches that are for alkane type alcohols like this. So this particular one might be what we'd see for this kind of OH. And then you've got this kind of OH, which is very broad, which is usually characteristic of an OH connected to a C double bond O. So these are typically strong, but the the OH stretch itself will go a very long way across the top of the spectrum. So far, in fact, that if you'd see this peak here that's at about 3000, this particular OH stretch has actually even begun to mask that peak. So what we're seeing there is effectively we've got our OH stretch, but sticking down through the OH stretch at about 3000, you've got these peaks here. So it's masking peaks that are up here as well, peaks we won't even see now because the OH is covering them up. The NH2 and the NH stretches, again we're talking about the H's moving in and out from the nitrogen. The NH2 kind of looks like vampire teeth. You get these two peaks at about 3300. And they're usually medium in strength. They don't usually come down a very long way. Medium to possibly weak in strength. The NH stretch looks a lot like the one of the NH2 peaks. So you'll just see a single peak for the NH stretch. And the way that you can distinguish an NH from an OH is that an NH is going to be weak to medium and won't be nearly as broad as our OH stretch. I'll just go back and show you that. There's your OHs, very broad, very strong. And the NH stretch, fairly weak or moderate in strength. So all of those, the NH2s, the NH and the OH, will all appear pretty much in the same region of the infrared spectrum at around 3500 to about say 3300. Looking at the next region, we're looking at the 2900 to the 3100 region. This is where we're going to find our typical CH stretches, and we're going to be looking at two specifically. We've got the CH stretch when it's connected to a CC double bond, and we've got the CH stretch when it's connected to a CC single bond. So we're only talking about the stretch of this particular bond, and it turns out that it's going to be at higher frequency when it's connected to a double bond and lower frequency when it's connected to a single bond. So this usually appears at about 3000 to 3100. And this one will appear at about 2900 to 3000 wave numbers. A lot of this has to do with the strength of the bond. Because this bond is shorter, it tends to be stronger because of the sp2 hybridization. This is sp3, so it's a longer bond, not quite as strong, so it will vibrate at a lower frequency. The shape of the peaks around the 3000 region then will thus give us clues as to the kinds of CC bonds we have in our compound. If you're looking at a peak and it only appears at just below 3000, so you're looking at the grouping of peaks here, everything's below 3000, then you can pretty much bet that the only kinds of CC bonds you have in your compound will be CC single bonds, because all you're seeing are CH stretches connected to CC single bonds. So that really gives you very good information. If you're looking at the peak at around 3000 and the peaks tend to straddle 3000, that means you've got peaks on both sides of 3000, indicating you've got both kinds of CH. CH connected to CC double bond and CH connected to CC single bond. This would indicate that your compound had a combination of CC double bonds and CC single bonds. It's pretty rare for a compound just to have CC double bonds in it. So these are the two cases we usually see. One where everything's below 3000, indicating the presence of just CC single bonds, and one where it straddles 3000, indicating the combination of CC double and CC single bonds. But we're only talking about a fairly narrow range here in between 2900 and 3100 wave numbers. The next region is the 2000 to 2300 region, and this is where we see C double bonds, C triple bond Cs and C triple bond Ns. Your C triple bond Cs usually appear at 2100 to 2200, C triple bond Ns about 2200 to 2300. These frequencies vary a little bit, but what we usually see are medium to weak peaks on the C triple bond Cs and medium to strong peaks on the C triple bond Ns. They're always sharp peaks though, and this is definitely what I'd call a diagnostic peak. If you see something in the 2000 to 2300 region, you've definitely got a C triple bond C or a C triple bond N. If you do not see a peak in this region, that's going to indicate you do not have either of those peaks or at either of those functional groups. The C double bond O region is the 1700 to 1850 region. This is where you'll see the C double bond O stretches. Again, a very important diagnostic region. A peak present in this region indicates a C double bond O. A peak absent in this region indicates the compound has no C double bond O. Very important region for you to look at. 1700 to 1850. Now there's two kinds of C double bond Cs that we'll be interested in. The first one is what I'm calling a C double bond C in a chain, So it'd be something like this. And so C double bond C chain. And the other one is a C double bond C that's part of an aromatic ring. Or sometimes you might see aryl, which means the same thing. Alright, so what we're going to see is that a C double bond C that's part of a chain will usually be around 1650 wave numbers, and a C double bond C that's part of an aromatic ring will be around 1500 to 1600 wave numbers. So aromatic rings will be at typically lower frequencies for their C double bond C stretches. The reason for that is because if you look at an aromatic ring, it's subject to resonance, and often we see the aromatic ring presented with a circle, indicating that the double bonds are not really true double bonds. They're actually spread all around the ring, and they are then not really full true double bonds. Because they're not full true double bonds, they will vibrate at lower frequencies. So these you'll find at about 1650 when it's in a chain, and at around 1500 and 1600 if it's a C double bond C that's part of an aromatic ring. Unfortunately, in the 1500 to 1600 region, you begin to see other things occurring as well. So it's not really what I'd call a diagnostic peak because of its the possibility of mixing it up with other peaks. But if you know you've got a C double bond C in your compound, and you might know that if you go back to this region, and you know you've got C double bond Cs because you see peaks between 3000 and 3100 due to a CH connected to a C double bond C, then what you could do is look down in this region and see what kind of peaks you see in the 1500 to 1600 and the 1650 region, and that will allow you to possibly be able to identify what kind of C double bond C you might have. All right, let's take a look at the next one. There are two possible C double bond O's that you might have in a compound. You might have an aldehyde or you might have a ketone. I mean, this is when you've just got C's and H's present as well. Now, a ketone is not going to have anything present here, but an aldehyde, you may see, or you probably will see, the CH stretch connected to a C double bond O. And this typically appears in the 2700 to 2900 region as two peaks. So what you'll see for an aldehyde is this CH stretch, whereas for a ketone, since we've got two C's connected to a C double bond O, we won't see anything in the 2700 to 2900 region typically. So that's how we would distinguish an aldehyde from a ketone. But again, we would only know this if there was a C double bond O present in the compound, because both aldehydes and ketones contain a C double bond O. So we can use these peaks in the 2700 to 2900 region to identify whether or not we have an aldehyde or we have a ketone.